Okay, welcome to class. It is our second to last real class. I think you're all very sad, as am I. We will have regular class tonight, regular class on Wednesday, and then Monday will be a review class session. So there will be no new content on Monday of next week. We will go ahead and get started with some of the questions. I will tell you something about the logistics here in a couple of minutes as well. And actually, let me connect to my iPad so that we can all see what I need you to see. Close and start iClickers. In progress. What? Do you see, if you go to iClicker, does it show a class session that just started tonight? Maybe it starts at 6 if I don't start it. Does it look like a new session for tonight?
It does for me.
Okay. But it shows as a new session, not as a session from like last week continued. No, I'm sure I shut it down. Okay, should be good. All right, then I am going to open that up. Resume the session. And we should be good to go. Full screen. Zoom up here. Yeah, there is, for those just joining us, there is a worksheet that I posted at about 5 p.m. I didn't put up as early as I normally do, and I didn't send out the announcement, so I apologize about that. But there is a worksheet. If you go to class content like normal, you should be able to see it in that folder in Blackboard. That's where I always put them, and then the announcement, and I just usually link out to it. So log into Blackboard, go to content week 14, and you should see the worksheet for tonight there. Okay, we have our first question posted tonight. Tonight is all about thermodynamics, and this is the idea of how energetics underlie all of chemistry that we've talked about so far. So really, you could say that all of the year worth of general chemistry that we've learned is to prepare us to talk about this part of the year. It's basically to say like, okay, great, all this stuff happens, but how much does it happen? When does it happen? And what do we do with all of it? So the question I have up now, right now, is this idea of spontaneity of a reaction. And it's really important that we talk about the direction that a reaction is written. So for instance, this reaction I'd be talking about here, we're saying that we have some reactant going to some product. When we're saying in the forward direction, we're always saying we're from reactants to products. That's considered the forward direction. The reverse direction is the opposite direction, right? So go ahead and submit your clicker response. And we've got 16, I think we have more than 16 people. Make sure you're logged in, submit a response. And we're split almost 50-50 on this. So this is really a definition type question. So Gibbs free energy for a reaction that's spontaneous in the forward direction is referred to as a negative Gibbs free energy. So delta G is the change in Gibbs free energy as the reaction proceeds. That change in Gibbs free energy, if it's negative, it means that we're moving in the way the reaction is written. We're going to form products over the course of that reaction, moving towards equilibrium. Okay, so that's just setting the stage for terminology. What would you then say would be the Gibbs free energy for a reaction that's already at equilibrium? Go ahead and submit your answer for that one using the same choices. Couple more seconds. All right, uniform. All right, delta G equals 0. That means that we're a reaction that energetically has reached the most stable mixture. It means that we have the exact amount of reactant and product mixture that is the most favorable. And so that means we have a Gibbs free energy of 0. So we'll keep that in mind kind of as we move forward. We'll look at it from a ton of different angles. We're going to look at it from electrochemical potentials of cells. We're going to look at it from a thermodynamic standpoint with enthalpy and entropy. You did that in the pre-class primer, so we're not actually going to touch on that very much. And then we're going to talk about our equilibrium constant and where we are compared to equilibrium constant. Is Q equal to K? Is Q not equal to K? That all ties in. So the big picture of kind of why we're doing this and where we're going. I hope this image looks familiar. You probably would have seen this in a biochemistry class or even a basic biology course. The idea is we're taking glucose as an energy source for metabolism. We then break that glucose down, and in the end, pops out the far side here is CO2 and water. It's basically a combustion reaction, but instead of just lighting it on fire and watching it burn, our body takes careless effort to do it over a number of reactions. And in doing so, we end up storing energy as NADH, ATP, and both of those molecules and FADH2. So these molecules are basically taking the chemical energy that's stored from stronger bonds. When we break those strong bonds, we end up with, we break weak bonds, we end up with strong bonds at the end. And that energy that's made available is stored in other molecules that are easier to access and move around the body. Each one of these little steps right here, the glucose molecule is becoming less and less and less stable. To do that, we have to put energy in. When we put energy into the system, it's not favorable. So to do that, somehow we have to drive a reaction in a non-favorable direction. And so we do that by tethering it to another reaction that is favorable. So it's this whole idea of playing with, it's like when you're using your cell phone, right? Your cell phone releases the electrons, no problem. You're using it, and then the battery dies. When your battery's dead, it's not favorable to recharge that battery by itself. So we have to connect it to the power grid, something that's going to be favorable, releasing electrons so that your battery can actually do something that's not favorable and refill the battery. Same exact concept applies here, except these are chemical bonds and your battery is electrical electrons that are moving. So we're going to look at that principle of how do we force these reactions to go in a non-favorable direction by tethering them to reactions that are favorable. And Gibbs free energy, so this axis right here is change in free energy, delta G, that Gibbs free energy we were talking about. So we're forcing delta G to go in a positive direction, which is not favorable, by tethering it to reactions that are actually favorable at the same time. If we looked at those individual little steps at the beginning there, this is what's happening to the actual chemistry. So we're breaking a carbon-oxygen bond here, and we're breaking apart the ATP molecule. We get ADP and then the other, so we have two phosphates, third phosphate sits here on this molecule. So we're forming new bonds. We're making overall this molecule less stable, this molecule more stable. So by making this one more stable, we drive this step forward. Same thing when it comes to this next reaction here. And so each one of these is this play where we have to put energy in order to get energy out. And then at some point we get a chemical reaction that releases a ton of energy and we generate an NADH. So all of your biochemical reactions that you're looking at are highly favored by tethering it to something that is going to drive it forward. At the end of class on Wednesday, by the end of class on Wednesday, you're going to be able to convert mathematically the Gibbs free energy of a reaction, relate it to the standard potential, electrochemical potential of a cell, stuff that we did last week in class. And you're going to be able to relate both of those to the equilibrium constant. And so these three reactions are kind of at the heart of how all of chemistry relates back together. I'll post these slides after class so you don't have to frantically write down these equations, but these are going to be really useful to kind of convert between everything. If you notice, all of them have this little circular symbol here, the delta G and the E cell, and we're going to be spending a lot of time today in class to talk about what that little circle means, and that is not always going to be there. So we have to pay attention when it is and when it's not there. So our learning objectives for today is to predict whether a reaction is spontaneous by comparing Q and K. We've already done this, but now we're going to talk about it in terms of energetic consequences. So is it going to be a positive Gibbs free energy, negative Gibbs free energy, or delta G is 0? And we're going to be able to have you look at that and actually mathematically calculate those values. And so that forces us then to talk about what standard conditions are and non-standard conditions, because you might have seen some in your homework and you will see a lot more. We can go in the back of a book and we can look up these standard values. This tells about a reaction, a lot of details about a reaction energetically that might not apply to our situation. So we're going to be really thoughtful about what does standard conditions mean, when can we use that, and when do we have to think about non-standard conditions. From these standard conditions, Gibbs free energy at standard conditions, that's what this little circle means. I want you to be able to draw a Gibbs free energy diagram, which we've done in class before, but we're going to bring those back. And then we're going to talk about where the minimum of the diagram is, how Q relates to that. And by the end of the week, as I showed you that triangle, I want you to be able to do is convert easily between all three of these different values. Any one of them will basically give you insight into the other two. Logistically, I wanted to put a couple things out there. Exam 3 is going to have a majority of the focus on acid equilibrium. That means titrations, that means buffers, that means ice tables, that means taking negative log of the right thing. So in order to help give you some practice, I did put up some practice assignments on OWL. You probably saw those. They're ungraded. There is no credit for completing them. However, if you want to check and see if you know how to go through these problems, I highly recommend that you go and you practice those problems that are up on OWL. I think it's called week 13 practice acid base, week 13 practice titrations and buffers, something along those lines. So use those as a resource. It's probably way better than if I just gave you a Word document with problems, because this way you get feedback and you get directions and you get to see how it's solved. And so it can help you kind of work through some of those kinks. Thanks to some help in office hours today, I learned that you couldn't actually see your weighted grade in OWL. I wish someone had told me that a lot sooner. I would have fixed it. So now if you go into OWL, you can actually see the percentage. I did already import those every once in a while into Blackboard, but you didn't get to see the exact updated percentage. So I just made a couple things visible that should have been visible, and now you can see it. And I should have thought about that and doing that at the end of class, because I see everyone like frantically like looking and clicking onto OWL right now. So don't go look at it right now. We got lots of stuff to do. More important stuff, your final grade in the class, right? I want you to have as much information as you can to decide whether you do credit, no credit next Monday night. To help you with that, I'm going to release exam 3, which will be available Wednesday right after class. You will have until Monday night to complete that. What that means is by the time you have to decide credit, no credit option, you will know what your exam 3 score is. As soon as you take the exam, you'll know your exam 3 score. It won't tell you which questions you got right, and there might be some reasons that that's not ideal to make it open all the way until Monday night, because you can't use it necessarily as a study tool for the final exam until after Monday night is passed, because I can't let you take it and then have everything shown, because then it'd be easy to just share it with someone else. So it will only give you your score, but at least that way you can use the grade estimator and you can figure out what your final grade in the course could be based on final exam scores that you think you would have. A final note about grades. I noticed that last week, I also sent an announcement, but the post-quiz scores were the lowest I've seen. There were some very difficult questions in that post-quiz. And so it was partially done on purpose to make sure to give you some of the hardest questions possible in that post-quiz, so that you can go back and you can review that post-quiz. And if you understand those questions in the post-quiz, then you're probably going to do really well in titrations and buffers. So please go back and study through that. Also go back and study exam 1, study exam 2, which is on OWL. You should be able to get access to see all the things that you've worked on there previously before you take the final exam. Remember, exam 3 is the last third of the course. Basically, we left off exam 2 right when we started equilibrium. So calculate the equilibrium constant was the last thing we did for exam 2. So everything from calculate equilibrium constant until the end of the semester, that's on exam 3. Exam 4, though, is cumulative over the entire semester. So if you were shaky on any of the stuff earlier, make sure to spend some time, go work on that material, because that's going to be on the final exam. And if you do better on the final exam than any of your other 3, your final exam score will replace your one lowest exam score. So if you did poorly on one exam, your final is the way to kind of make up for that. All right. Any questions on final exam or logistics before we move into the rest of the course material?
When is the final exam?
It's a good question. I am tempted to release the final exam on Monday. So in theory, if people really wanted to, maybe let's do this. Let's do a clicker question to see if anyone actually used this. So let's do, I'm gonna do a multiple choice clicker poll. I'm gonna write your options on the screen. And as you look at that question in my chicken scratch handwriting, hopefully you can read it. I'll read it out loud in a second. The question is, if I open the exam Monday morning and close it Wednesday night, it will be open for 3 days. I want to know, would anyone actually use it on Monday? The reason I'm asking is because there's a review session where our class would normally be a week from tonight. So I anticipate that very few people would, if anyone, would take it before that final review session. One reason you might want to take it earlier rather than later is because then as soon as you take it, you'll know your final exam score and you can calculate your grade for the whole semester, and you can use that to decide credit, no credit, or to take your letter grade. So go ahead and click in your answer. Would you take it on Monday? It will probably be 3 to 4 hours is the window of time. I'll leave it open. I'll let you, once you start, you'll have 3 or 4 hours, but it will be open through the regular final exam date that's scheduled. So does anyone need another second to click in their answer if they would or would not take it on Monday?
Do you know when the lab exam is?
There is no lab exam.
Oh, they like canceled it?
Yes, as far as I know.
Oh, bet. Okay.
I'm 95% sure. I think Lauren is pretty upset. Okay, let me go ahead and check the poll results, see what you all said. 5 people said that they would take it Monday. Okay, so that is the plan then. I will have the final exam ready to open Monday morning at midnight, basically Sunday night, Monday morning. So you can take it anytime Monday through the end of the day on Wednesday. Our originally scheduled time is Wednesday evening from 6 to 8 p.m. Once you start the exam, you will have to complete it within, I think, I'll probably give 4 hours. I'm not worried about time. The thing that I'm going to do that might be a little bit weird is that before you click on it, you're going to have to click on a Google form. And it's basically an honor code signature, if you will, that you will take this exam on your own. You're not going to share the exam with anyone else or help anyone else on the exam. Just basically a thing I'll have you click just so it's present in the front of your mind when you take this exam. It's worth the same as the other 4 exams, other 3 exams for the semester. So there shouldn't be a reason, like it's not worth half of your grade, but if you do well on it, it can help you. So I just want to make sure that that we stay honest, that I get to see what you're capable of, and I'm happy to help you in any way I can to make sure you do as well as you possibly can. There's a chance I could do a review session on Saturday or Sunday. I'll probably send out a poll to see if people would like to have that. All right, any other questions? Nope. No,
Dr. Bailey?
yes.
I'm sorry, just like for the sake of time, to save some time when we study for the final exam, do you recommend going back over the old exams and like the homework questions?
Yes. I think that you should be able to retake exam 2 as practice. That will be a good way to see what you do and do not feel fresh on for that. exam 1, I think, is posted with an answer key as well. So that might be a good way to kind of go back and look through some of that material. I usually don't recommend going back and taking homework assignments as practice if it's been 2 or 3 weeks, because you remember how to start it. But the assignments from longer ago, you don't remember how to start it, it's gonna be a good way to test yourself. The practice assignments that you might not have done before are gonna be really good to work through. There's been a few throughout the semester, I believe, on a couple different topics. And then once you find a topic that you know you need to work on, that's when it's going to be really valuable to go back and either use the POGL activities that you might not have used, or there's extra POGL activities that are suggested in the far right column of the schedule. And that's a really good way to work. I would also really advise trying to find other people in this class to study with. So maybe I'll try to find a way to kind of allow you guys an opportunity to create communities to study. If you know people in class, great, maybe from lab. Otherwise, there might be ways I can figure out. Maybe put in the chat window if you'd like to be part of a study group, and all the names there I'll take and I'll send a group email to everyone. That's probably a good way to do it. Okay. Any other questions? All right. Feel free to email me with any questions or post the Blackboard discussions as well. So let's go ahead and get back into our discussion on Gibbs free energy. So we're going to bring out some terms you probably remember from biology: exergonic and endergonic. Which one of these is exergonic? Graph on the left, top left, or graph on the bottom right? All right, I've got 19 responses. Judging by the responses, there's a lot of confidence in this. Does that sound about right? Not much confidence. Okay. What is exer? So the two options are endo and exergonic. Endo means into. You have to put energy into it in order to make it go. Exer means out of, so releasing energy. So based on our discussion earlier on, if we have a reaction that is spontaneous in the forward direction, it's going to have a negative Gibbs free energy, and it's going to release energy. So our term for endergonic is the top one. That means inputting energy. And then the bottom one is exergonic, and that's releasing of energy. So that's a negative Gibbs free energy. If we take that concept and we look at a reaction, a chemical reaction, we can kind of look at this chemical reaction. We've seen this graph a number of times throughout the semester. We're combining two reactants to make one product. If we start at time 0 with only our two reactants, we can let those react together, and over time they create this pink product here. If we talk about this with kinetics versus equilibrium, our left side is how fast does a reaction occur. We use this to discuss that for every 1A that's being consumed, 1B is being consumed, and 1C is being produced. So we can figure out the rate of reaction, we figure out the rate of production. On the right side, we talked about equilibrium, constant K. What is the final proportion of products to reactants, and what's the most stable? So for Gibbs free energy, we're going to talk about the fact that this on the left side is negative Gibbs free energy all the way up until the point where we get to equilibrium. And then once we get to equilibrium, we know how Gibbs free energy is equal to 0, that there is no more energy left that can be harnessed from this reaction. This reaction here has energy that needs to be released in order for it to get to equilibrium. So I want you to look at the worksheet that I sent you all. And for those who might have joined since the last time I mentioned this, it is on Blackboard under content for week 14. So I have 3 identical Gibbs free energy diagrams here. I want you to think about, shake off the cobwebs. It's been a little bit since we talked about these. These represent one chemical reaction. reaction. And I just made 3 copies of it across the screen here. On the left side of the reaction has not gone. So I said the extent of the reaction is 0. And remember, this is what we're talking about is, if we use the last reaction as an example, we have this reaction that goes. If the reaction has gone 0%, it means that we have only reactants. If it has gone 100%, extent of reaction is 100%, then we have all products or 100% products. So the 2 ways to look at the x-axis is 100% reactants on the left, 100% products on the right, or you can say extent of reaction is 0 on the left side, extent of reaction is 100% on the right side. So go ahead and mark the 2 spots on each one of these graphs. Put an X where the most stable mixture exists. And that's where our equilibrium constant K is going to be represented. And then on the far left one, I want you to show where Q would be on the dotted line. And all of these are going to be on the dotted line somewhere. So each one is going to have an X and a circle. The X is for the most stable mixture, and then the circle is going to be on the far left one where Q is smaller than K. Q is equal to K on the middle one, and Q is greater than or larger than K on the right. So let's make sure everyone's on the same page working through this. Can I have a volunteer to tell me where we're going to put the X on these graphs? And actually, you might even be able to annotate. Can someone annotate and put the X on the graphs? Is that an option? Can I have a verbal volunteer first before we have it written on the screen? Does anyone even remember how to use these? Maybe, maybe not. All right, let me try putting an X on one of these and see what you guys think. What do you think about the red X that I drew? Is that the energy minimum, which is where our equilibrium constant would be, 100% products? Amber's shaking her head, why not? Where would you put it? Anyone want to volunteer? Do I have any voices? Anyone?
So there for that middle one, the X and the circle are both going to be at the bottom of the line, right?
Why?
Because that's going to be the most stable spot energetically.
Fantastic. So this is, we talked about this before, as if kind of think about, you have a ball that kind of sits on this line, it has gravity, and so it's going to move to the most stable part of that dip. And so no matter if you start with all products or all reactants, that you're always going to find your way down to the most stable mixture. And so that most stable mixture is where our equilibrium constant is going to be found. So our equilibrium constant K is always going to be at that most stable mixture. And if you notice, this Gibbs free energy is something we're going to pay a lot of attention to. So I'm going to use two different colors. I'm going to use red and purple. So our equilibrium constant is the bottom there. And for this one, we said Q is equal to K. So we're going to put both of them on top of each other. So I'm going to go ahead and mark our equilibrium constant in all three of these. It's the same reaction, same minimum. So then can I have a volunteer? Let's see. I think I might call on, let's see, Tracy, would you like to pick either the Q is smaller or Q is larger and tell us where the circles can be?
On the Q is smaller than K, I would assume it's going to be to the left of the X.
Why?
Because that's it's less, I don't know.
So remember, Q and K, both of them are all about the concentration of products over the concentration of reactants. And so if we're saying Q is smaller, it means that there's a larger proportion of it on the bottom, on the denominator. That means the reaction has proceeded less far, or we're closer to 100% reactants. So I agree with you. I would put the circle to the left when Q is smaller than K. And in the case where Q is larger than K, that can be anywhere here to the right of that red X. Now, I'm not saying that everything to the right of the red X is the same Gibbs free energy change, because in order for any of these to reach equilibrium, that circle, that Q, is going to change in order to get to K. In doing so, the vertical height that it falls down to get to the height of the red X, that's how much Gibbs free energy is released or capable of being released for that reaction to proceed towards equilibrium. So in the case of the one on the far right, what's our sign of Gibbs free energy for this reaction here? Taylor Gamble, any idea what the sign of Gibbs free energy is when Q is larger than K and the reaction proceeds towards equilibrium?
When Q is larger than K, would G be greater than 0?
Why?
Because energy is being released.
That's
So-
true, but that's true on both of these graphs. In both the far left and the far right, in order for that Q, the ball, to get to the bottom, energy is released. The question is, which direction does a reaction run in order for Q to change to get to K? So which one of those is positive and which one is negative? I'll give you a hint. The one in the middle, delta G, is equal to 0 because we're at equilibrium. Maybe that's not a very useful hint.
So would the right one be positive?
Why?
Because it's greater than 0?
What does a delta G greater than 0 mean?
Means it's non-spontaneous.
Okay, but let's be more specific. So the full wording of that first question is,
It requires energy for it to happen.
the one little part of that first question you're missing is in the forward direction. So if a reaction is spontaneous in the forward direction, Gibbs free energy is negative. So which one of these has a spontaneous reaction in the forward direction? Because you can argue that both of them are spontaneous, right? Both of them are going to fall down to get to K. So which one is going to have a spontaneous reaction in the forward direction while the reaction proceeds to K?
The far left graph.
So in order to get to equilibrium, this one has to proceed from reactants to more products as it also releases Gibbs free energy. So that's going to be a negative Gibbs free energy on that far left side. The one on the far right, that one is going to also be spontaneous, but only in the reverse direction. We're only taking products and making reactants if that is just let go and it reaches that most stable mixture of reactants and products. Okay, so that idea of delta G is negative when a reaction is spontaneous in the forward direction. That's going to be the flagstaff. That's going to be what we always keep coming back to through the rest of class today and the rest of the class on Wednesday. It's going to really help if you just remember negative Gibbs free energy change, spontaneous in the forward direction. All right. So we have our kind of definitions here. One little morsel of suggestion I have for y'all is a lot of people just tried to memorize if Q is smaller than K, it's this. If Q is bigger than K, it's this. If you can visualize these Gibbs free energy diagrams, it's going to be so much easier than memorizing. Because honestly, I'll tell you, year to year, I used to try to memorize if Q is bigger than K, what's the sign of Gibbs free energy? And I can never remember it. If you just can picture these diagrams and see that, okay, if Q is on this side, it's going to proceed in a forward direction. The only thing I have to memorize is that negative delta G is forward direction. And then everything else you can just do from the graph. So hopefully that'll help. All right, so I think we've kind of gone through these three questions. Q is larger than K, the reaction is spontaneous in the reverse direction. So that's basically saying our Q is out here. There's an equation that lets us calculate this as well. Was this in your primer or is this in Wednesday's primer? I can't remember if this was in today's primer. Okay, so this idea that Gibbs free energy is equal to R, which is the gas constant, 8.314 joules per mole times Kelvin. That's our gas constant R. Temperature is always in Kelvin. It's always going to be a positive number. You can never have a negative number there. So then what decides the sign of delta G is the natural log of the ratio of Q over K. So I think we're pretty bored by this right now at this point in the semester. What does natural log of 1 equal? Anybody? What is log of 1? Natural log, doesn't matter which log you're using. Thanks, Sydney. Okay, so that's a reference point. So that goes back to the last diagram we had. Jesse said that if Q equals K, they're right on top of each other, we're at equilibrium, right? That means that Q equals K, so that ratio of Q over K is equal to 1, right? So natural log of 1 is when Q equals K. Gibbs free energy equals 0. We know that. Gibbs free energy equals 0 when we're at the minimum. We have no energy to give in the forward or backwards direction. Then if we have Q is larger than K, I don't always remember this. So I grab my calculator and I say natural log of, I don't know, 2, right? 2 over 1. And I get a positive number, 0.693. If I do natural log of a fraction that's just less than 1, where Q is smaller than K, natural log of, let's say 0.75, I get negative 0.28. So this reference point of when Q equals K, we have Gibbs free energy equals 0. If we have more of Q, it becomes positive. If we have more of K, K is bigger than Q, then it becomes a negative number. Then that all feeds back in to delta G. So if you have this one equation, it tells you that the only thing that matters to determine the sign of how much free energy is available, whether the reaction is going forward or backwards, is just the ratio of Q to K. Then this becomes a really useful equation. But you guys are really good with logarithms, right? So let's manipulate this equation. Let's do a different version of this equation. So another way to write out ln of A over B, it's the same thing as ln of A minus ln of B, right? We can undo the fraction by writing it out as 2 logs. And then if these were multiplied by, I don't know, star, then it becomes star ln of A, star minus star ln of B. So that distributed property applies. So a way to simplify, or I would say another way, I really like the version of the equation that I have on the left because it talks about the ratio of Q to K. But another way to write this equation is, like we just said, we can split it out. RT ln of Q minus RT ln of K. Both of these forms of the equation are extremely valuable, and I'll show you why in just a minute. So with those in mind, let me see if, let's do a mathematical comparison and see if these numbers play out. So go ahead and click in a numeric value of what you think your equilibrium constant K would be for the graph that we've just been looking at. So if you were to approximate, is K 1? Is it 10? Is it 100? Is it 0.1? Is it a negative number? Can it be a negative number? You want to do a 60-second breakout for this? Thumbs up for breakout, thumbs down for no breakout. All right, we're about 50-50. We'll do a 60-second breakout. I'm going to send you to breakout rooms, and then I'm going to immediately hit stop so that you can automatically send. Uh-oh. There we go. So the problem is that now I have multiple. All right. Did y'all get a chance to submit your response? All right, I think everyone got forced back. Make sure you submit your response, put in a number you think is a reasonable number for your equilibrium constant K for this Gibbs free energy diagram. Couple more seconds. And it looks like our okay, we had our most popular answers were in the ballpark of 0.1 to 0.3. Can anyone who answered that describe why you might choose 0.1 to 0.3 as your equilibrium constant for this? Anyone willing to share? It's like pulling teeth tonight. Help out. Some new voices, please. Is it better to call on people? Go ahead, Carter.
So I said it'd be less than 1, just because it's closer to the side of the reactants. If it was closer to the side of the products, then it would be greater than 1. But it's not. It's closer to the side of the reactants. And it's just kind of eyeballing it. It looks like it's I'm halfway, about 0.3. And if it was even further to the left, then it would be closer to, it's closer to 0 than it is now. So.
Great. So I love that you came back to this idea of, Carter, you mind killing? I'm going to mute you. I think you got a phone call going on there. This idea that is about the concentration of product over reactants. And so the further we are to the left when we're at equilibrium, the larger the bottom is. And so in this one, I kind of eyeballed it and I approximated, I don't know, what does that look, about 20% complete? So that means that we have 20 to 80 would be our ratio of products to reactants, something along those lines. And if you do that math, it's about 0.25 is that ratio. So I don't really care the exact number, but I want the logic that Carter gave, that the number has to be compared to 1. If we had a minimum of 1, it means the minimum is right towards the middle of this graph, about an equal mixture of reactants and products. In this case, we had more of the reactants. The minimum lies to the left, meaning it lies towards reactants. And so that gives us a pretty good idea of that number. Okay, so if we, let me see where the next clicker question goes. All right, so with that Gibbs free energy diagram, we said we have approximately a K of 0.25-ish. Let's now think about, there are infinite number of Qs that could be in existence. We could have this mixture of reactants and products, or we could have this mixture, or this mixture, or this mixture, or, right, any of these dots on the line could be a mixture that you could find somewhere. And then you could say, okay, to get to equilibrium, this reaction would proceed to the left, proceed to the right, or it's at equilibrium. And remember, the further it drops down to get to equilibrium, the more Gibbs free energy is released, the bigger the magnitude of that number is. So let's take a look at one standardized value. The idea that I'm going to tell you, hey, this reaction does this, expect this for energetics. You're not going to tell me what the specific concentrations you used. It's going to be so difficult. So what we've done is we've kind of standardized this. And we've gone and said, let's just talk about everything in standard temperature and pressure. And this idea of standard temperature and pressure, we denote it with this little circle. So the terminology is delta G naught. That naught refers to that little degree looking symbol, and that means standard conditions. So you can also say E cell naught. So E cell naught. So naught means 0. It means no number. And that little symbol is the symbol we use for standard conditions. So standard conditions means that everything is always going to be reported at 25 degrees Celsius. Any pressures that exist are 1 atmosphere. And the most important thing for us right now is that any concentration is always going to be 1 molar. All right, so keep that in mind, because we're going to be comparing delta G naught and delta G, right? Delta G can be from any Q, but delta G naught is saying specifically, if we're at Q in this scenario, what happens to get to equilibrium? So we're going to go ahead and make this a clicker question. So the clicker question is, if we're at standard conditions, what is our Q value? Go ahead and submit your response. And then we're going to go ahead and close out. Looks like we're about 50% of the class is in agreement here. So 50% of the class thinks that the answer is C. Who disagrees with that and why? Why is C the majority, but the wrong answer in this case?
I said B, but I said B because Q and K are both products over reactants, but it doesn't say that it's at equilibrium at standard conditions.
Fantastic. So this idea that Q is always a concentration of products over reactants, honestly, it doesn't matter what the stoichiometric coefficient is. It's just 1 raised to that power. So when we're at standard conditions, that's just saying, regardless of where that minimum is, the minimum might lie to the left, might lie to the right, but we're going to be saying, well, we're going to look from a perspective of Q equal to 1. That's it. So let's take a look at, let me see if I have it in this graph. I do not have it. So I'm going to redraw the Gibbs free energy diagram that we just had. Something like this, right? Where is my Q value going to lie on this graph? Here's my K value, right? Where is standard conditions? Where is that comparison point I'm going to be making for everything else? Where is Q when Q equals 1?
Directly in the center of the line.
So here's what people did. They said, it's so hard to compare when everyone's using different concentrations. Let's just have everyone report as if it was 1 molar concentration. So we're going to say, we're going to look at every single graph, Gibbs free energy diagram, as if we had 1 molar concentrations. And then I can tell you that Gibbs free energy, not, right, standard conditions, 1 molar concentration, if that is being reported for this graph here, then it's positive. Why did I say that Gibbs free energy at standard conditions for this graph is positive?
Is it because it's product favored, or it's on the right side of the X there?
Yes. So I'm going to take the second half of what you said there. So our standard conditions are to the right of the most stable mixture. That means in order for this reaction to get to that most stable mixture, it actually has to go backwards. So from that standard right down the middle, we're not at equilibrium. So delta G is not 0. In order to get to that most stable mixture, we have to backtrack and take products and make them reactants. So I would actually flip the first thing that Alex said. This reaction is reactant favored. It's reactant favored because our equilibrium lies to the left. However, our Q value, Q equals 1, is to the right of that, so it has to backtrack to get us to equilibrium. Does that kind of connect what you're saying, Alex?
Yes, that was much better.
Okay, that's why I get paid to do this. Okay, so delta G naught is this crazy thing that actually tells us what the diagram looks like. So if I just told you delta G naught is positive, you automatically know that this is what the graph looks like. The graph has a minimum that lies to the left. If I tell you delta G naught is negative, that tells you the exact opposite. It tells you that the minimum is product favored, the reaction lies to the right. So there's a lot of information that comes in just knowing the sign of delta G at standard conditions. It tells you where the minimum is compared to the center. The other thing that is nice about standard conditions is if we go back and we look at that equation that I wrote out, I said both of these are awesome, right? And I'm going to use this one for a second here. Delta G equals RTL Q minus RTL K. If we have standard conditions, what is this Q value? Standard conditions, Q is?
The 1?
1. Okay. So we're going to say at standard conditions, right? I have to put a standard in there if I'm making Q equal to 1, that we put a 1 in place of that Q. What's the natural log of 1? 0. So it simplifies. This whole side simplifies to 0 only at standard conditions, right? Only at standard conditions. And then we're left with delta G naught equals minus RT ln K. So think about that. And I know that this is something that chemists get really excited about, but it's super cool. I'm a chemist, so I can get super excited. If we go and we look in the back of a book and we pull up a delta G naught value, that not only the sign tells us that the reaction lies to the right or to the left, but if we do that and we know what temperature, right? We know what temperature is, standard temperature, right? 298 Kelvin. We know R, right? That's a constant. We can find out the equilibrium constant. We can find out how far to the right or how far to the left the reaction lies just from delta G naught. That calculation is straightforward. You just have to know how to do e to the, and then you can figure it out. All right, so that's part one. We're gonna come back to where else that becomes really awesome and how the equations fit together. So if we already talked through this, if we have delta G naught that's positive, we have our Q value right in the middle. And so at standard conditions, the reaction delta G naught positive means the reaction lies to the left. So remember that magnitude, that how big, not just the sign tells us right or left, but then how big it is tells us how deep that plunges from standard conditions and how far to the left or how far to the right that minimum is. Okay, so the big picture that we were talking about, if you kind of picture this as maybe your cell phone battery when it's dead, that your cell phone battery started out fully charged, but now we're at the bottom of this hill energetically. How do we get that reaction to go? We have to tether it to another reaction that has Gibbs free energy that's going to be spontaneous when we let it go. And so here's the idea that we're tethering together two different reactions. A lot of times the reaction that we use over here is ATP being broken down into ADP and phosphate. We had water as a component there too. You have to use water. So that reaction is used to give off enough energy to drive a lot of reactions in a non-spontaneous direction. So where that delta G is depends on delta G naught, but it also depends on the concentration of the reactants and products. All right, I'm gonna jump over this. I'm going to have you all back in the breakout rooms. It's been way too much of me talking. So I'm gonna move us into breakout rooms and I want you to calculate the equilibrium constant for this reaction, given only the information that you have here. Submit that as a question. And I'm going to send you all to the breakout rooms if I can get this to go. I'll see you back here in about 2 to 3 minutes.
We got it figured out, Dr. Bailey.
I love how I mute myself and I forget when I come back from the room. I don't know why it does that. We only have 12 clicker responses. You guys all clicked in? Y'all? All right, we're up to 13 responses. We'll give it a few more seconds before we start walking through it. I feel like Josh's group lost their facilitator. Is that true? He just like peaced out. Come on, Josh. Maybe he said something. I don't know. Okay, I think we got everybody back. So can I have someone very briefly summarize the steps needed in order to solve this? And don't put numbers in there, just talk about the terms and how we know to use those. Maybe Sam, can I have you share with us?
So what we did was we just basically filled in for the equation. So we were trying to find K, but we had Gibbs free energy. We knew the
Caveat, we had Gibbs free energy at standard conditions.
right at standard conditions. And so then we knew the standard conditions of 298 degrees Kelvin, and then the other constant. And so from that, we were able to solve through the equation to find K.
All right, so the equation you're referring to is delta G naught equals minus RT ln of K. We know standard conditions, so even if I hadn't told you the temperature, you would have known 298 Kelvin because that's 25 degrees Celsius, that's standard conditions. We know our R, 8.314, joules per mole Kelvin. Okay, and then the only thing we plug in a value and then we can find what our K is. Two things that people I think might have done wrong. One of them is in the end, we can solve for ln of K and we have to do e to the whatever that number is. And let's go through and look at what the responses are and see if anyone else fell in the other pitfall that sometimes people do. I'm gonna go ahead and, if you haven't already submitted your answer, please do so. All right, it looks like a lot of people did fall into this pitfall. So we have our values, we can plug in all of our values and we get ln of K equals 12.314. Does that look like what you got for your values? Uh-oh. So what might we have forgotten to do? What is that face, Tina?
Well, yeah, that's what I was telling Diane, that I got 12.3 also. I forgot ln of K in the front.
Okay, so you forgot to do the final step, which is e to the, and then
e to the, yeah.
Sydney, what else did you notice that I saw your face kind of do one of these? Ooh.
We forgot to convert to joules.
Right. So our units for R are 8.314 joules. And this equation releases a ton of energy, literally 1,000 times more. So that kilo is times 10 to the third. So if you do forget that, you're going to end up with a number that doesn't really have any relevance to the problem at all. So be really careful to always write out your units whenever you're working through problems like this. So then if we do e to the 12.314, we get our equilibrium constant to be 2.23 times 10 to the fifth. And it looks like we might have our chat. What did someone say in the chat window? And negative R. Yes, agreed. So we might forget the negative sign in the front. we might forget the kilojoules, and then we might forget to do the last step to get our K value. And so it looks like we had 6 people, maybe 7 people answer this correctly. There's one more, but very few people went through those steps appropriately. So the most common answer, I guess that was one of the most common answers, but a lot of people got 1, which I imagine is what happens if you basically do negative 30.5 here. So we have negative over negative, and so those 2 negative values will cancel out and give you, am I doing this right? No, it's a positive value, right? So positive 12.316 and e to that. So does this make sense? What does the Gibbs free energy diagram for this look like? So go ahead, I think that's my next question for you all, is go ahead and draw a Gibbs free energy diagram for this reaction. Go ahead and take 30 seconds or 1 minute. So draw your little bucket, put your Gibbs free energy diagram in that. Think about where the minimum should lie. Verda, can I get you to share what your graph looks like?
I didn't actually finish drawing mine.
Just describe it.
So I put the Q on the right hand side, and then it would have been more towards the center. If this making sense.
So I'm going to have you be a little bit careful. Gibbs free energy at standard conditions, our Q is always equal to 1. So that should always be our reference point. So if we have our Gibbs free energy is a negative 30.5 thousand joules, then I guess let's see what the whole class says as far as where the minimum is going to lie. Is it going to lie to the left? Is it going to lie to the right? Or is it towards the middle? Go ahead and click in your response briefly. Couple more seconds. And closing out. So 2/3 of the class says that it lies to the right. The way that we know that is that we're at Q equals 1, right? Standard conditions. We're right in the middle, Q equals 1. From that position, we have a negative Gibbs free energy. That negative sign says that in order to get from Q to our equilibrium, the reaction has to run forward in the direction it was written spontaneously. And actually, if I could draw this better, it would probably, the minimum would be like tucked over here in the corner, because 30.5 thousand negative is really, really far to the right. This reaction, another way to say it, is that our equilibrium constant is way, way, way bigger than 1. Meaning when we're at equilibrium, we're going to have almost 100% products, as another way to say why it should be to the right. So hopefully you're starting to see that both your K and your delta G tell you where the minimum lies. If it's a K of 1, your minimum lies in the middle. If it's less than 1, it's to the left, greater than 1 to the right. Delta G naught, the sign tells you which side your minimum lies. So if we had non-standard conditions, where would Q on your diagram be? And these non-standard conditions was 10:1 ratio of reactants to products. So 10 times more reactants than products. Go ahead and click in your response. Oops. I think I messed something up. Hopefully you guys can see it. Couple more seconds. All right, closing out. So here we're basically saying that we have a lot higher ratio of reactants. So our Q is off to this side. So I agree with a slight majority of the class that Q would be left of the middle because Q equals 1 is right down the middle. So then the question is, for those exact conditions we just talked about with this Q that's way over the left, how does the sign of Gibbs free energy compare to when we had standard conditions? Remember, standard conditions was Q equals 1. Now we're Q equals this up here. Is the sign the same as delta G? Is the sign opposite, or is delta G now 0? Go ahead and submit your response. Couple more seconds. So we have a majority of people that say the sign would change compared to delta G. So can I have someone that answered A share why the sign would stay the same? We have 3 individuals.
I said it would stay the same because the Q value didn't move to the right side of the K value. It just moved more left. So it would stay negative because the reaction is still moving in the forward direction.
Great. So Q equals 1 was in the middle. Q equals whatever this number is, I guess 1 over 10, is still on the same side. So in order to reach equilibrium, both of them have to proceed in the same direction, meaning the sign of your Gibbs free energy is both going to be negative, as well as your delta G naught we said was negative. In this case, what does change about delta G though? What's different about delta G compared to delta G naught between these two? Same sign, what does change?
The value of the delta G of the reaction.
Does it become bigger? Is delta G bigger or smaller than delta G naught?
Smaller.
I'm going to disagree with that one. In order to get to equilibrium, which is down at this height here, delta G has to drop way more than delta G naught had to drop in order to get to equilibrium.
But it would still be negative, right? Would it just be like negative 130? Or would it be like...
So delta G, in this case, I don't know, maybe negative 150 kilojoules per mole, when delta G naught was negative 30.5 kilojoules per mole. Because
So
we're so much, go ahead.
Technically be smaller because it's still negative.
Sorry, I forgot the negative sign there. Yeah, no, small means closer to 0. So that number is further
like
away
smaller,
from
it's
0.
like negative 150 is smaller than negative 30, right? No?
I mean, I understand where you got that, but no, that's not the definition of smaller. The definition of smaller means closer to 0. It means you have less Gibbs free energy to give away. Okay.
Okay, I got it. Sorry.
So that is our class for tonight. We're going to spend all of Wednesday's class as well working on how Gibbs free energy and equilibrium constant also relate to electrochemical potential of a cell. So feel free to stick around if you have any questions about what we did in class tonight, or if you want to schedule something for the next couple of days to chat and catch up about this last section of class. Hope you have a good night.